In this video, we're going to apply our understanding of exponential equations to the more difficult extended response style questions. We will start by overviewing the key information that these questions are likely to provide, and then how you can use that information to create your own exponential. From there, we'll cover the key examples that cover the vast majority of extended response style questions. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The general form of the exponential is written above. You might notice that the terminology used is a little bit different. Overall, the exponential still works as you remember it. We've only changed the name of the term so that they better suit the application style questions. Let's take a look. The term n0 is usually referred to as the initial value of your exponential. Now, initial value in the context of extended response style questions just means the starting value at time t equals 0. If we sub t equals 0 into the generic exponential equation, after a bit of simplification, we see that all the other terms disappear, leaving us just with n0. It's for this reason that the coefficient out the front, n0, is referred to as the initial value. Just a quick note on this. If your exponential also has a vertical translation, then this doesn't necessarily hold quite as well. If you sub in t equals 0 into this, you're going to have both n0 and c, your vertical translation. This is very rare though, I just thought I'd mention it just in case you get one of those crazy questions. All else being equal, the base of an exponential dictates how fast or how slow the exponential is going to rise or fall. Take, for example, the following exponentials. We have 2 to the power of x and 3 to the power of x. For the same value of x, 3 to the power of x is going to rise much faster than 2 to the power of x will. In the context of extended response questions, you're going to pick your base to be equal to the growth rate of your scenario. In this example here, we're told that the number of cells in our sample is going to double every 15 minutes. The fact that it's doubling every fixed period means that our base is going to be 2. If we had said tripled instead, then our base would be 3. It's easiest to think about this coefficient as being responsible for fixed periods of growth. Using the earlier example, if I wanted to double every 15 minutes, then my k value is going to be 1 over 15. To complete the equation, we're just going to assume that our initial value, n0, is equal to 1. Now, let's see what happens every 15 minutes. If I sub in t equals 0, I get n equals 1. As expected, it was the initial value, and so when I sub in t equals 0, I should get the initial value. But when I sub in t equals 15, I get 2, which is twice as large as 1 was. If another 15 minutes elapses, I would sub in t equals 30, and in this case, I get 4. Once again, we've doubled the previous amount. One thing I want to highlight here is that this exponential is purely in terms of minutes. That might not always be the case. I mention this because most of the time your denominator for k is just going to be 1. Think about doubling every 1 year, or 15% increase every 1 month. In both cases, your coefficient k is going to have a denominator of 1, and therefore the entirety of k is going to be 1. The only thing that does change is the unit that your time is in. In the first example, it was in years. In the second example, it was in months. The only time you're going to see a difference in k is if you suddenly start doing something like 2 months, in which case your denominator is going to be 2. Okay, let's try some examples. First up, we're told that our population of bacteria is tripling every 20 minutes. The first step in these scenarios is always to figure out what is the equation that explains this scenario. First, we're told that the initial population size is 1,000, so our coefficient n0 will also be 1,000. Next, we're told that we are tripling our number every fixed period, and so our base is going to be 3. Furthermore, that fixed period is 20 minutes, hence our coefficient k is going to be 1 over 20. Just like that, we've created the equation. Once you have the equation, you can answer pretty much any question you want. The most common one is to figure out when a population is going to reach a certain threshold. In this case, let's suppose that we want to know how long it's going to take for our population to reach 15,000. Well, if 15,000 is our final value, then we can replace capital N with 15,000 and just solve for t. These will always be CAS questions, so we're just going to plug it into the solve, and then that's our answer. When we solve this, we're going to see that our time taken is going to be approximately 175 minutes. If it doesn't say it around your answer, then be sure to give the logarithmic closed form answer instead. Questions about decaying exponentials are often written in terms of radioactive materials. Let's take a look. First off, we're told that the initial mass of our radioactive material is 10 grams. Hence, our coefficient n0 is going to be 10. In this case, there actually isn't enough information to choose a specific base. With that in mind, we're just going to choose any base we want, and it's still going to work out. My recommendation is to choose a base of 2, because it makes solving for k a little bit nicer. Speaking of which, solving for k is a matter of subbing in a known point, and then cas solving for k. In this case, the point that we're given is the fact that we know that the half-life is 24,000 years. For those who didn't study chemistry, the half-life is just the time it takes for a radioactive material to decay to half of its initial mass. So, in math speak, it means it took 24,000 years for us to go from a mass of 10 grams down to a mass of 5 grams. Or even more specifically, it means at t equals 24,000, n equals 5. When we plug that into the cas and solve, we're going to see that our k value is -1 over 24,000. See the pattern? That's the advantage of choosing a base of 2. Now that we have k, we've figured out the rule of our exponential. This question in particular is asking us to figure out how long it's going to take before our radioactive material decays to 10% of its initial value. So basically, this means we want to figure out how long it takes to go from 10 grams down to 1 gram, since 1 gram is 10% of 10 grams. So we're going to sub in n equals 1 into our equation and then solve on the cas, and that's going to give us a time of approximately 80,000 years. Oddly enough, in some circumstances, you don't actually need to know the initial value of your exponential. We can actually look at the previous example and strip that information away and still be able to solve it. The reason why we can still solve this is because all the information given to us is in terms of percentages rather than fixed amounts. What we do is skip right to the part where we start solving for k. And to do that, we're going to replace n, our final value, with half of n naught, because that's what it is. Doesn't matter what n naught was, we know that the final result is going to be half of whatever it was before. And when you look at this equation, you'll see that you have n naught on both sides. Those cancel out if you divide both sides by n naught. And just like that, you don't have to worry about what that initial mass was. From there, if you plug this into the cas, you're still going to get the exact same k value from before. Once again, to answer the actual question, we need to go back and find, okay, how long does it take to get to 10% of the initial value? Well, instead of saying half the initial value, we're now saying 1 out of 10 of the initial value. Once again, the n naught terms cancel out, you plug into the cas, and you get the same answer. So I just want to reiterate, this only works because everything was written purely in terms of percentages of the initial value. If it said, find how long it takes before you have 2 grams left, you wouldn't be able to answer this. It needs to be a percentage. Sometimes, the information that you're given doesn't necessarily one-to-one translate to one of the exponential terms. Under these circumstances, you can just use simultaneous equations with 2 known points on the curve. In this case, it's going to come from the fact that we know that after 1 year, our population is 52, and after 3 years, our population is 80. Those are 2 known points on our exponential curve. From there, we're just going to get the cas to solve it simultaneously. On the TI Inspire, this is going to be found under Menu, Solve, Solve System of Equations, and then Solve System of Equations again. You're just going to set the number of equations to 2, and then plug in the variables as you see fit. From there, you just plug the equations in and get your answer. If you're using the Casio instead, it's under the Math 1 tab. You're just going to click the button that's highlighted there. Once again, still plugging in those exact same points. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool. You should check it out. I'll see you there.